Clearly, the spring is exerting some force in the upward direction to keep that mass from going down to the table, right? So we know that force is there. If we compress the spring to a bunch of different distances by putting, say, different size weights on it, we can then solve for the spring constant just the way before we solved for pi. So it just so happens, not quite by accident, that I've got some data from the spring. So let's look at it. So here's some data taken from measuring a spring. This is distance and force. Force computed from the mass, basically, right? Because we know that these have to be in balance. And I'm not going to ask you to, in your head, estimate the constant from these. But what you'll see is the format is there's a distance, and then a colon, and then the force. Yeah. Oh. Right. Yes. Thank you. All right. You want to repeat that more loudly for everyone else?
Yes.
Right. Right. But the x in the equation, right, here we're getting an equilibrium. Okay. So let's look at what happens when we try and examine this. We'll look at spring.pi. So it's pretty simple. First thing is I've got a function that reads in the data and parses it. You've all done more complicated parsing of data files than this, so I won't belabor the details. I called it get data rather than get spring data because I'm going to use the same thing for a lot of other kinds of data. And the only thing I want you to notice is that it's returning a pair of arrays. Okay? Not lists. The usual thing is I'm building them up using lists because lists have append and arrays don't, and then I'm converting them to arrays so I can do matrix kinds of operations on them. So I'll get the distances and the forces, and then I'm just going to plot them, and we'll see what they look like. So let's do that. There they are. Now, if you believe Hooke's law, you could look at this data and maybe you wouldn't like it. Because Hooke's law implies that, in fact, these points should lie in a straight line. Right? If I just plug in values here, what am I going to get? A straight line, right? I'm just multiplying k times x. But I don't have a straight line. I have a little scatter of points. Kind of it looks like a straight line, but it's not. And why do you think that's true? What's going on here? What could cause this line not to be straight? Have any of you ever done a physics experiment? And when you did it, did your results actually match the theory that your high school teacher, say, explained to you? No. And why not? Yeah? You have various kinds of experimental or measurement error. Right? Because when you're doing these experiments, at least I'm not perfect, and I suspect at least most of you are not perfect, you get mistakes. A little bit of error creeps in, inevitably. And so when we acquired this data, sure enough, there was measurement error. And so the points are scattered around. And this is something to be expected. Real data almost never matches the theory precisely, because there usually is some sort of experimental error that creeps into things. So what should we do about that? Well, what usually people do when they think about this is they would look at this data and say, well, let me fit a line to this. Somehow say, what would be the line that best approximate these points? And then the slope of that line would give me the spring constant. So that raises the next question. What do I mean by finding a line that best fits these points? How do we fit, in this case, a line to the data? First of all, I should ask the question, why did I say let's fit a line? Maybe I should have said let's fit a parabola, or let's fit a circle. Why should I have said let's fit a line? Yeah. Well, how do I know that the plot is a linear function? Pardon? Well, so two things. One is I had a theory. So, I had up there a model, and my model suggested that I expected it to be linear. And so if I'm testing my model, I should try and fit a line, my theory, if you will. But also when I look at it, it looks kind of like a line. So, if I looked at it and it didn't look like a line, I might have said, well, my model must be badly broken. So let's try and see if we can fit it. Whenever we try and fit something, we need some sort of an objective function that captures the goodness of a fit. I'm trying to find, this is an optimization problem, the sort we've looked at before. I'm trying to find a line that optimizes some objective function. So a very simple objective function here is called the least squares fit. I want to find the line that minimizes the sum of observation sub I, the ith data point I have, minus what the line, the model, predicts that point should have been, and then I'll square it. So I want to minimize this value. I want to find the line that gives me the smallest value for this. Why do you think I'm squaring this difference? What would happen if I didn't square the difference? Yeah. Positive and negative errors might cancel each other out. And in judging the quality of the fit, I don't really care deeply. You're going to get very fast to roll your question candy here. I don't care deeply whether the error is which side it is, just that it's wrong. And so by squaring it, it's kind of like taking the absolute value of the error, among other things. All right. So if we look at our example here, what would this be? I want to minimize, I want to find the line that minimizes it. So how do I do that? I could easily do it using successive approximation. Right? I could choose a line. Basically what I am is I'm choosing the slope here, right? And I could, just like Newton-Raphson, do successive approximation and for a while and get the best fit. That's one way to do the optimization. It turns out that for this particular optimization, there's something more efficient. You can actually, there is a closed form way of attacking this. And I could explain that, but in fact, I'll explain something even better. It's built into PyLab. So PyLab has a function built in called polyfit. Which, given a set of points, finds the polynomial that gives you the best least squares approximation to those points. It's called polynomial because it isn't necessarily going to be first order. That is to say, a line, it can find polynomials of arbitrary degree. So let's look at the example here. We'll see how it works. So, let me uncomment it. So I'm going to get K and B equals PyLab.polyfit here. What it's going to do is think about a polynomial. If I give you a polynomial of degree 1, you've all learned that it's ax plus b. B is the constant and x is the single variable. And so I multiply a by x and I add b to it, and as I vary x, I get new values. And so polyfit, in this case, will take the set of points defined by these two arrays and return me a value for A and a value for B. Now here I've assigned A to K, but don't worry about that. And then I'm going to now generate the predictions that I would get from this K and B and plot those. So let's look at it. So here it said that K is a 31.475, etc. And it's plotted the line that it's found. So I've plotted the line. You'll note a lot of the points don't lie on the line. In fact, most of the points don't lie on the line. But it's asserting that this is the best it can do with the line. And there's some points, for example, up here, that are kind of outliers, that are pretty far from the line. But it has minimized the error, if you will, for all of the points it has. That's quite different from, say, finding the line that touches the most points, right? It's minimizing the error, the sum of the errors. Now, given that I was just looking for a constant to start with, why did I bother even plotting the data? So I happen to have known before I did this that polyfit existed. And what I was really looking for was this line. So maybe I should have just done the polyfit and said, here's K and I'm done. Would that have been a good idea? Yeah. right, well, one of the things, exactly right, that says, well, how would I know that it was fitting it badly or well? And in fact, how would I know that my notion of the model is sound, or that my experiment isn't completely broken? So always, I think, always look at the real data. Don't just, I've seen too many papers where people show me the curve that fits the data and don't show me the data. And it always makes me very nervous. So always look at the data as well as however you're choosing to fit it. As an example of that, let's look at another set of inputs. This is not a string. It's the same get data function as before. Ignore that thing at the top. I'm going to analyze it, and we'll look at it. So here I'm plotting the speed of something over time. So I've plotted it, and I've done a least squares fit using polyfit, just as before, to get a line. And I put the line versus the data. And here I'm a little suspicious, right? I fit a line, but when I look at it, I don't think it's a real good fit for the data. Somehow, modeling this data as a line is probably not right. A linear model is not good for this data. This data is derived from a more complex process. So take a look at it and tell me what order of polynomials you think might fit this data. Or what shape does this look like to you? Pardon? Quadratic, because the shape is a what? It's a parabola. Now, I don't know if I dare try this one all the way to the back. Ooh. At least I didn't hurt anybody. All right. Fortunately, it's just as easy to fit a parabola as a line. So let's look down here. I've done the same thing, but instead of passing it 1, as I did up here as the argument, I'm passing it 2, saying instead of fitting a polynomial of degree 1, fit a polynomial of degree 2. And now let's see what it looks like. Well, my eye tells me this is a much better fit than the line. So again, that's why I wanted to see the scatter plot, so that I could at least look at it with my eyes and say, yeah, this looks like a better fit. All right, any question about what's going on here? What we've been looking at